Okay. Uh-huh.
How did you question?
Uh, yeah, it's the force on the charge is just going to be Q times the electric field. So that's the electricity and magnetism stuff.
Right.
But it's a constant acceleration problem, so you have to use kinematics from I 111. Yeah, last semester. Yeah, yeah. All right, good morning, everyone. So the usual announcements, homework 3 is due tonight. And then I think everyone should have, whoever's registered in the tutorial, you would have had your first tutorial this week. And so we'll do tutorial 2 next week. Also, all lab sections have run, so we finished lab 0. You'll do lab 1 next week. Make sure that you complete your pre-lab before you show up to lab 1 next week. I noticed some of you have already submitted that first pre-lab, so that's great. Okay, so and then quiz number 1 will be during Wednesday's class of next week. Okay, so what we were talking about was this idea of electrical flux, and so we're imagining placing some kind of surface. It could be a physical, like real surface, or an imaginary one, but we place it in some region of space where there's an electric field. And what we worked out, or maybe perhaps what we defined, is that flux is proportional to the number of electric field lines that cross that surface. And so we thought about a variety of cases. The easiest case was a flat surface in a uniform electric field. And in that case, if the surface, let's say this is my surface, was exactly perpendicular to the electric field, then you get the maximum possible flux, and just given by E times the area of the surface. So that's a flat surface perpendicular to a uniform electric field. And then what we did is we said, okay, let's start to relax some of those restrictions. Let's say we're still going to keep our electric field uniform. We're going to keep our surface flat. So this is a side view, but we're going to allow there to be an angle between the electric field and that surface. What we ended up doing was defining a unit vector n hat. It's also called a normal unit vector because it's perpendicular to the surface. And we use that normal vector to define this area vector. The magnitude of the area vector is just the area of the surface, and the direction is perpendicular to that surface. Okay, and in that case, we could write the flux as the dot product between the electric field and this new area vector, which is equivalent to saying that it's E times A times the cosine of theta, where theta is in blue there. It's the angle between our normal vector and the electric field. Okay, and then lastly, we said, all right, let's now be completely general. Let's have an arbitrary electric field. It doesn't have to be uniform or constant. It can be changing direction and magnitude at all points in space. And we're not going to have any restrictions on our surface. It could be curved surface at any angle with respect to that electric field. That's in general a more challenging calculation, but our idea was to divide the surface into small little patches. And so I've highlighted one of those patches shaded red, and we could say, well, if we make our patch small enough, then our surface will appear to be flat, and the electric field will be approximately uniform over the area of at least that small patch. And then so for that small patch, we could say the electric field is going to be E times dA, dA being the area of that small patch, times the cosine of the angle between the normal vector and the electric field at that position of that patch. And then what we're going to do is we're just going to add them up for all the little patches that we need to form our complete surface, and we would get the net flux that we could express as this integral. Eventually, we will get to Gauss's law, probably in the next couple of classes, and one side of Gauss's law is going to be this expression for the flux, the integral of E dot dA. What we're going to do is we're going to find a new way to calculate the same flux, and then we're going to say these two methods for calculating the flux have to be identical, and that is going to be Gauss's law. Okay, there was a good question last class from over here, and it said, the question was, can we have negative flux? And the answer is yes. If the normal vector and the electric field have an angle greater than 90 degrees between them, then when you do this cosine of the angle, cosine of some angle bigger than 90 degrees is going to be a negative number, right? So for angles between, I should say, 90 and 270 degrees, you would get a negative result for that cosine. So the rule of thumb is that if the normal vector and the electric field are kind of approximately parallel, or like more parallel than they are anti-parallel, then those parallel ones have positive contributions to flux. If the normal vector is approximately anti-parallel to the electric field, then you're going to get negative contributions to the flux. And that's going to be important for what we're about to talk about. Okay, so what I want to do today is let's now consider a closed surface in an arbitrary electric field. Okay, so I'm going to try to draw a closed surface. I'm going to make it a cube. Yeah. What's that? Oh, the mic. Oh, okay. Thanks. Let's see. Let's see if that's a problem I can resolve. So when we talk about these closed surfaces, we're going to imagine, or we're going to make a distinction between electric fields that are going to be entering the closed surface and those that will be exiting the closed surface. So let's see here. Okay, I think we're back in business. Thank you. All right, so what I'll do is I will draw a closed surface. I'm going to make it a cube because that's one that I can draw without too much trouble. And so let's see, we'll have some hidden lines in here as well. Okay, so that's approximately a cube. Now, the first thing that we're going to have to do is we're going to have to make a definition for our unit vector. And that definition is going to be when we're dealing with a surface that's closed, so it has like an interior and an exterior, then we're always going to define our unit vectors to be pointing outwards. Okay, so for closed surfaces, we define our normal unit vectors such that they point outwards. Okay, and so I'm going to draw that for the closed surface that we have here for our cube. And what we're going to, a cube has 6 surfaces, right? 4 sides and then a top and a bottom. And so we can draw 6 different normal vectors for these 6 parts of our closed surface. And so let's see, we'll make this top surface the first one. And so we'll say that's n hat 1. Let's see, I'm going to make 2 the bottom surface. So we'll do dashed and it comes out here. This is n hat 2. And then we just keep going. Here's 3, let's say. 4 is going to be over here. N hat 4. And then 5 will be this front one. And then this one's harder to draw, but we've got this back one, which will be n hat 6. Okay, and so there's all of our normal vectors for a closed surface pointing outwards, right? We could also have drawn a sphere, and then we would have radial normal vectors, but they'll always point out, okay? So now what we're going to do is we're going to place this in an electric field, and we'll see if we can think about what the flux must be in this case. So I'm going to draw just a few electric field lines, just so that our figure doesn't get too messy. So here's one electric field line. We'll have it cross the enter in from the left-hand surface and then exit out through the top. And then we'll have another electric field line coming in, penetrates through, and then punches through again over here, and then I'll draw one more. It comes through, and then maybe it'll punch out through the bottom here. Okay, so the first question is, what is the net flux through this closed surface? Well, what we know is we're going to have positive flux when the electric field is approximately parallel to the normal vector. And so if we look at N2, so if we look over here, we're going to get a contribution of positive flux, where this red electric field line is approximately parallel to the N2 normal vector. Over here, we'll get more positive flux, because close to N3 hat, we've got this red electric field line coming out. And, you know, they're not exactly parallel, but they're more parallel than they are anti-parallel. And then over here, we'll have a small but positive flux here. So here, N1 and the electric field they're almost perpendicular. If they were exactly perpendicular, the flux would be 0, but they're not. They're a little bit away from perpendicular, but so we get a small bit of flux there. But then when we go and look at these lines that are entering the surface on, you know, I guess it's on your right, they're coming into the right, then we would say over here we have negative flux in all 3 of these cases, because the electric field is moving left to right, but n hat 4 for that surface is pointing to the left, and so they're anti-parallel. Okay, so we have some positive contributions and we have some negative contributions. And then we also know that flux is proportional to the number of lines crossing the surface. And so what we could say is, I've drawn 3 lines that exit our surface, and I've drawn 3 lines that enter our surface. So what then would be the net electric flux in this case, do you think? Any guesses? If I have just as many, yeah, go ahead. It cancels out exactly, that's right. So it's going to turn out that if electric flux, as we interpreted last time, is equal to or proportional to the number of lines crossing a surface, then we would say every time we have an electric field exiting our surface, we're going to get some positive flux, but it's going to be exactly canceled by all the electric field lines that enter our surface and contribute negative flux. Okay, so on the left, n hat 4 points left, while E points right. And so therefore, the angle between n hat 4 and the electric field is approximately 180 degrees. And so when we go to evaluate this dot product between the electric field and the area vector for that left-hand surface of our cube, what we're going to end up with is the electric field dotted with whatever the area is and this normal vector, and that's just going to be the electric field times the area times the cosine of, approximately 180 degrees. And so this is going to be approximately -1, and we'll get a negative flux. Okay, so when the electric field and our normal vectors are anti-parallel, they contribute negative flux. Okay. On the other hand, when the electric field and the normal vectors are approximately parallel, and so that means the angles that we're thinking about are like between 0 and 90 degrees, then we're going to get positive contributions to the flux. Okay. And then what we noticed and what we'll write down is that for our cube placed in some arbitrary electric field, we have the same number of electric field lines entering and exiting our closed surface. So notice that the cube surface has 3 field lines entering. So that's negative flux. And 3 field lines exiting. And so that's positive flux. And so the net flux through this closed surface is 0. Okay, so what we're going to do is we're going to keep making these similar kinds of arguments for different types of closed surfaces and different charges placed around it. So we'll start with a very similar example. So let's think about a point charge next to a closed surface of any shape. So it doesn't have to be a cube or a sphere or whatever. I'm going to try to draw like a Cheeto, and we'll see what it looks like. So our Cheeto or our cat poo looks something like this. And so I'll try to draw like it's kind of got a shape to it, right? So it's got some structure. It has kind of these cross-sectional areas, circular like. Okay, so there's our Cheeto, a closed surface. It's like a little bubble. And then I'm gonna place a point charge next to it. And whoops, so we'll make our point charge here. We'll start with a positive point charge, Q greater than 0. I'm gonna move it so that it's a little bit closer to my Cheeto. Okay, so there it is. And all I'm gonna do is I'm gonna draw the electric field of this point charge. We know that the point charge creates a radial electric field that looks something like this. And so now what we have is we puncture through our Cheeto here and exit out this way. And then over here, we enter and then we exit on this other side. And then over here, we're going to enter and then exit over here. All right. So there's our Cheeto next to a positive point charge. And just like for the cubed surface, we have the electric field entering in 3 points and exiting in 3 points. And so there's going to be some negative flux contributed when the field enters, and we're going to have some positive flux contributed when it exits, and those will balance exactly. So once again, this is a scenario where the net electric flux is exactly 0. So we could say, since the same number of electric field lines enter and exit the surface, the net flux is 0. Okay, now what I could do is I could take this point charge and I could move it around to different positions. And as long as it's not inside of our surface, wherever I put it on the outside of the surface, it's always going to contribute 0 net flux. I could also take my Cheeto and I could bend it into different kind of shapes, right? I could distort its surface, but as long as it remains a closed surface, however I distort it, as long as there's no charge inside, I'll always have 0 net flux. So for a closed surface of any shape with any charge outside of it, you're never going to get any net flux. That doesn't mean the electric field is 0. We can see that the electric field at the surface is not 0 at a bunch of places, but the net flux is 0 because we get that cancellation from fields entering and exiting our surface. Okay, so any charge distribution outside a closed surface of any shape contributes 0 net flux because all field lines enter and exit the surface. Okay, so what's the only way? How could I get a situation where I have a non-zero flux to a surface, closed surface? What do I have to do? Yeah. Yeah, so let's move the charge inside. Okay, and so let's think about a charge inside a closed surface. Okay, so I'll go back to my cube for no particular reason other than it's easy to draw. So here's my cube. And some hidden lines in here. And let's put our point charge right in the middle of this cube. So this is inside, Q greater than 0, let's say. And now if I draw its electric field, it's going to punch through in a bunch of places, like so. Okay. So I'll draw a few more. I don't want to draw a million of them, but I'll draw, I guess, a few. Okay, good. Now, if I was to draw all the normal vectors again, I won't put subscripts, but I'll just draw the 6 normal vectors. Then we see that at all the surfaces, the normal vectors and the electric fields are kind of parallel-ish, or they're more parallel than they are anti-parallel. And so what we're always going to get is only electric field lines exiting our surface. They're all contributing positive flux, and we'll get some non-zero flux greater than 0 in this case. Okay, so in this case, the field lines only exit the surface, exit the, let's say, the closed surface, and we only get positive flux. And so here, phi is greater than 0. All right. What would happen if I put a negative charge inside a closed surface? Would I get positive or negative flux? Negative, right? We have only electric field lines entering the surface. They would be anti-parallel to the normal vectors, and they would all give these negative contributions. Yeah.
How is the closed surface always zeroing, like the angle? So the sheet of metal has an angle, has a flux. Why is not like maybe really thin rectangle?
Yeah, so it would turn out, so for any close shape you could draw in any electric field, you're right, if the field lines and the normal vectors are really parallel, you're going to get cosine of 0 is just 1, and then I think what you're saying is somewhere else I might have a different angle as to why those cancel exactly.
No, I meant like earlier we did like flat sheet of thing, electric field.
Yeah.
That did have a flux.
Yeah.
But if you like make it cube and make it really like you squish one of the side lines so it's almost 0,
yeah.
It's at least seems to me at least be like basically the same as the flat sheet.
Oh, sure. So yeah, so you're right. You're thinking of, you're making a distinction between 2-dimensional surfaces and then like a closed surface with a 2-dimensional skin enclosing a 3D volume, right? So I guess for that constructive sheet, what we're really thinking of is something that's infinitesimal, like it has no thickness. It's like there's no real physical object that is a 2D sheet. It always has some thickness, but we can imagine something with 0 thickness.
So it's flux for like normal objects that don't have a charge inside of them, always 0.
Yeah, for any physical object that has an interior with no charge in that interior, the flux will be 0. Yeah. Okay, good. So yes, so if we put Q less than 0 or negative in a closed surface, we get a non-zero flux that is negative. All right. Now, what I want to imagine is taking this charge in our cube we drew up here, And I put that charge right in the center. But let's say we're gonna keep it inside the cube, but we're gonna take that charge and we're gonna move it close to one of the corners. Is the flux gonna go up? Is it gonna decrease? Or is it gonna stay the same? What do you think? Stay the same, why? Yeah, and another way to say, I think, a similar thing is that we know that flux is determined by the number of field lines that cross a surface. So if I move this charge next to one of the corners, I'm going to redistribute what the electric field looks like inside the cube, but I'm not going to change the number of field lines that exit this closed surface, and therefore the flux would have to stay the same. So if we move the charge off center of the cube, we still have the same number of electric field lines exiting our surface exiting the closed surface, and therefore flux doesn't change. Okay, and so I could try to draw that roughly. So here's our cube. And now we'll take our charge and we'll place it over in this corner. And when I draw the electric field, I still have the same number of crossings. And so the flux doesn't change. Okay, so it's going to cross here. It's going to cross somewhere over here and over here and over here. Of course, this is the charge creates a 3D electric field. And so I've got field lines coming out the front and the back. That's too hard for me to draw. But we just have to imagine that as we move the charge around, we change the strength of the electric field on the surfaces, but the net flux does not change. All right. So the next thing we could think about is what would happen if I have this charge in my cube, this exact one here, and then I say, all right, I'm going to change this charge. I'm going to double its value. What's going to happen to the flux? Or what's going to happen to the strength of the electric field if I double Q? It's going to double, right? For a point charge, the electric field is K times Q divided by R squared. So if I double Q, the electric field doubles. If I double the electric field, the density of electric field lines has to double, right? Because the strength of the electric field is proportional to the density of field lines. So if I double the number of field lines, what happens to the flux? Is it going to go up or down or stay the same? I have a stronger electric field, more field lines. What happens? Yeah.
Wouldn't the additional field lines cancel each other out? So it could stay with the same.
No, they're not going to cancel each other out. They could only cancel in terms of flux if you had the extra field lines entered and exited. But what would those field lines could only exit if I double the strength of this charge, right? So let's draw it. If we double the value of Q in our surface, in our closed surface, the electric field doubles. And so we get twice as many field lines. And so let me draw a side view of that. Side views are easier to draw. So from the side, my cube just looks like a square. I'm going to put my charge over here. And so now I'm going to make this say like, this is going to be 2q, and it's going to be positive. So what I had when I had 1q is all of these field lines. So I think I was drawing 8 of them, wasn't I? So we'll draw 8 of them. Okay, so it's going to look something. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So that's originally what we had, but then we make Q twice as strong. And so the field gets twice as strong. And so that means the density of electric field lines has to double. So I have to draw now 16 of these things. And it's going to look like this. And when I'm talking about flux, I'm talking about the net number of field lines entering or exiting our surface. Here, we have only electric field lines exiting our surface, and so we would double the flux. So in this case, phi doubles because there's twice as many field lines exiting our surface. Okay. So let's draw one more example here. And so what we're going to do now is we're going to keep Q in a closed surface, but we'll do some funny things, right? We'll make our surface a funny shape so that we can get some different sorts of effects. Okay, so the next thing we'll do is, what if we change the shape of the closed surface? So I'm going to come back, I'm going to bring back our little Cheeto. And so I'm going to make this one pretty curvy. I'm going to try to at least. So there's our Cheeto. You know, again, it's got like these circular cross-section kind of things. And now I'm going to put Q over here. We've been choosing positive charges a lot. Let's choose a negative charge just for kicks. All right, so here's Q less than 0. And I can draw my electric field this time. For Q less than 0, the electric field lines point towards the charge. And so I'll draw a bunch of them coming in. So all right, and so this time we get something that's a little different than we've seen before. I still have a bunch of electric field lines crossing my surface. And here I'm drawing all of the ones that kind of come into my surface. And so I've got a bunch of electric field lines coming in, contributing negative flux. And so I have 8 lines coming into my surface, but I've got these 2 additional ones over here on like the little loop. And so I've got here, I have a incoming, and then over here, I have an outgoing electric field line. So what happens to these 2? How do these 2 contribute to the total flux in this case? Or do they contribute anything? I think this is, yeah, go ahead.
They're going to pass, no matter what happens, it's going to enter inside of the field, so it still contributes.
Yeah, but that's right. But so what we have is we have 2 that are coming in and 1 that is going out. And so the net result is if we're counting the number of field lines crossing our surface, one of the incoming lines or one of the incoming contributions cancels with the outgoing, but we still have the one left over that's coming in. And so whether or not we had that field, that one line punctures the surface 3 times, but the net result is it comes in once. And so we don't get extra contributions from these extra little pieces here. And so we could say one incoming contribution cancels with one outgoing contribution. And so if I drew a second little surface here that was like more sphere-like, and I had the same Q less than 0, and I drew these 8 electric field lines, in both cases for this little sphere and for our bigger Cheeto, they have the exact same flux. So we have the same flux phi in these 2 cases. Okay. So I think what we can do with all of these kind of observations that we've made is we can draw a conclusion. And the conclusion we can draw is that the electric flux is proportional to the charge enclosed by our surface. So we saw that if charge is outside, so Q enclosed is 0, there's no enclosed charge, then the flux is 0. If we bring the charge inside and then double it, the flux doubles. So flux is proportional to Q. If I take my charge and move it around inside the shape, there's no change in the flux. So flux is just proportional to Q, not where it's located. If I have the same charge enclosed in 2 different shaped surfaces, one complex and one simple, doesn't matter. The flux is the same. So all of these observations lead to the conclusion that the electric flux through a closed surface is proportional to the enclosed charge. Okay, in fact, there's one other thing that we observed that I didn't mention. If Q is negative, we get negative flux. If Q is positive, we get positive flux. And so it's still the case that Q enclosed is independent of, the flux is exactly proportional to the charge that is inside our surface. All right, so in the last couple of minutes here, what I want to do is I just want to preview what we're going to do with Gauss's law. So next time, we will derive Gauss's law. And so I'm just going to tell you what the result is going to be. The result will be that, 1, we already know that the flux is equal to E dot dA. Okay, that's what we did last time. What we're going to find is that the electric flux is also equal to Q over epsilon naught. We've already argued that it has to be proportional to the charge. What we'll have to show next time is that the proportionality constant is exactly 1 over epsilon naught. And so that implies that E dot dA is going to be equal to Q over epsilon naught for closed surfaces. So this is for a closed surface. I'm going to fix up this notation just a little bit. We have to be a little bit careful with how we write this because we could have a closed surface with some charge that sits outside. And in that case, the flux is 0. So I'm going to emphasize that this charge is enclosed by our surface. And so the little subscript is ENCL, stands for enclosed. So this is going to be enclosed. This is Q enclosed is the total charge enclosed by the surface. And I'm going to fix up one more little thing in our notation. And that's on the integral. So for our surfaces that weren't closed surfaces, they're open surfaces, like a little sheet or something like that. What we have to do is we have to integrate over the area of that surface. When we have a closed surface, we have to, again, it's the same thing. We have to integrate over the total area. But usually what people will do is they will put a little circle on the integral sign if the surface that you're integrating over is the closed surface. And so this is just to emphasize that we are talking about the special case of a closed surface. Okay, and so this thing will be Gauss's law. And what we're going to do is we're going to use this Gauss's law to calculate how the electric field behaves around certain types of charge distributions. In general, this integral is hard to evaluate, right? You could imagine, you could have a surface of some really complicated shape that's still a closed surface, but it wiggles and bumps and twists and turns, and it would be almost impossible to actually evaluate that integral. So what's going to happen is we're going to look for special cases where it's actually very easy to evaluate that integral. And the special cases are going to be cases in which the electric field and our area vectors are easy to evaluate the dot product. So we want them to be either perpendicular, so the dot product is 0, or parallel, so the dot product is 1. Okay? We're also going to look for cases where the electric field at our surface is constant. If E is constant, then we'll be able to take it outside of the integral. And we'll be left with just integrating dA, which just says, tell me what the area of the surface is. And then we'll be able to solve that and find what the electric field is. Yeah. Sorry, I can't hear you. People are making noise.
In the point where we are one incoming and one outgoing,
Yeah.
we know that the electric field is inversely proportional to the store resistance.
Yeah.
Isn't one line that is coming with the smaller population?
Yeah, that's a good question. So you're right. If your charge is close to one surface, the electric field will be strong there and weak at the farther one. But it'll turn out that the angles, like you have to do also a dot product. And so you're going to get these factors of cosine theta. And so you have different factors of cosine theta at different areas of the surface. You'll also have the area will be bigger in certain parts, and all of those effects will always cancel out so that there's one incoming and one outgoing. They'll always do that. Yeah. All right. So thank you very much. Have a good weekend. We'll see you on Monday.
Charge partially inside the field, partially outside of the field, or just half.